let's consider the following problem. Suppose we have a voltage source oscillating, and we have it connected to a resistor. And in here, we have a box, and we don't know what's in the box. But I want to put some criteria that inside the box, connected in, it could either be an inductor, or a capacitor, or it could be LC connected in series. So it could be both of them, or separately L or C. And what I'd like to do is try to figure out how to make some measurements and see what's in the box. So I'll make the following measurements. That suppose I measure at 6 radians per second. And I discover that the voltage, which we're going to write as Vt, V naught sine of omega t, and our current as I naught sine of omega t minus phi, I discover that phi1 is plus pi over 6. Now, that tells me that my voltage is leading the current. So this looks inductive for a positive phase when I write omega t minus phi. And my second measurement is when omega 2 equals 2 radians per second. And at this, I have phi2 equals minus pi over 6. And with the negative phase, my circuit is capacitive. Now, right away, that tells me that if I have these two measurements and the phase is going from a negative value to a positive value, that I must have both L and C. And let's just keep a little trig identity in mind that the tangent of 30 degrees, that's pi over 6, plus or minus, is plus or minus 1 over root 3. And to make our calculations simple, I'm going to say the resistance is root 3 ohms. Now, what I want to do is I'd like to find L and C. And I have two conditions here. And I've been given the phase values for both of those conditions. And I know in general that tangent of phi is omega L minus 1 over omega C divided by R. And so now you can see why I've chosen R equal to root 3 ohms. That for the case omega 1, when the phase is possible, I have 1 over root 3. And I'm going to bring my R over to the other side in a moment. So let's just put the R over here. That's omega L over 1 over omega 1c. And because R is root 3 ohms, I have my first condition that 1 equals omega 1L minus 1 over omega 1c. And now my second condition is here the phase is negative. And so I'm going to get same type of argument. I'll get negative 1 equals omega 2L minus 1 over omega 2c. So I have equation 1 and equation 2. And now you can see I have two equations and two unknowns, and I want to solve for L and C. So I'll set these two equal by multiplying this side by both sides by minus 1. So I get minus omega 2L plus 1 over omega 2C equals omega 1L over omega 1C. And now I can bring the L's, I'll combine terms, so I get omega 1 L. I'll bring that to this side, so I have L times omega 1 plus omega 2L. And that's equal to, bring those over there, bring these terms over to this side, and I get 1 over C times 1 over omega 2 plus 1 over omega 1. And what that gives me is I can simplify this thing to look like omega 1 plus omega 2 over omega 1, omega 2. And I have a very nice relationship that 1L times C is equal to, and the 1 over omega 1 C's cancel, and I just get that's equal to 1 over omega 1, omega 2. Now remember that because there's two L and C's here, we know that our resonant frequency, omega naught, which is 1 over square root of LC, I can now put that in here, and I get the relationship, if I square both sides of the equation, that 1 over omega naught squared, so dividing and squaring, and I get that's equal to 1 over omega 1, omega 2. And so my first result is I can figure out what the resonant frequency is of this circuit. That's 2 radians per second times 6. So that's the square root of 12 radians per second. And that's my resonant frequency in this circuit. Now next, we'll try to solve for L and C. Now, when we solved this equation, we found this nice result, which told us that C was 1 over omega 1, omega 2 times L. I'm going to box that result and look at what I can do with equation 1. I have 1 equals 1 over omega 1 L minus 1 over omega 1. Now C here, so 1 over C is omega 1, omega 2 times L. And so I have my condition here that 1 equals, notice the omega 1's cancel, so I get minus omega 1, omega 2 times L, or L is 1 over omega 1 divided by omega 2. Omega 1 is 6 radians per second. Omega 2 is 2 radians per second. So what I get is 4 henries for L. Now we're running out of space, but you can see for C down here that I have 1 over omega 1 times omega 2. That's, let's see, did I get this? This is not 4 henries, but 1/4 henry, because 1 over 6 minus 4 is 1/4. And if I put 1/4 in for L, and I multiply 2 times 6, 12 over 1/4 is 1/3. And so I get 12, I get 1 over 3 farads for C. So it's a little complicated, but that's how I can figure out, given this box with unknown elements and 2 measurements that gave me the phase constants at different frequencies, I was able to write down 2 equations for the phase constants, and that enabled me to solve for the resonant frequency, 1 over the square root of LC. And given the resonant frequency, or even just these 2 phase constant conditions, I can substitute C over L. I can solve these 2 simultaneous equations for L and back to C, and I get my results.